Thank you all for coming. I appreciate the opportunity to talk like this, and what we're going to go over is regional groundwater modeling and how you can use that in terms of surface water groundwater interaction. There's been a lot talked about this in the past, and I'm going to set it up by just sort of introducing the topic and then focus it on the actual tools that we use, and that's groundwater budgets and the concept of groundwater capture. I'll use GMA 11 as an example because our new groundwater availability model that we just completed actually helps with these features and with these analyses. And then at the end of the slideshow is a bunch of references that y'all may find useful down the road for your work. We've all seen this kind of cartoon cutaway of an idealized groundwater system where there's recharge and flow towards a river. And when a pump starts initially, it creates a cone of drawdown. Water is drawn into the well and it starts taking it from where it once went, and that was the river. But over a long enough period of time, now the river is actually supplying the well in part. So from a simple concept like that, we use groundwater budgets to define a specific area and look at inflows, outflows, and storage change. This concept started off, my research shows it goes back to at least the early 1930s. And in 1937, there's a famous textbook that talked about groundwater budgets, basically dismissed them because there wasn't enough data available, and the lengthy time that you would need to collect that data to get the full range of sufficient hydrologic conditions was limiting. So what are we talking about with a groundwater budget? You've got a groundwater system you define, whether it be a county, a region, a GMA, whatever. You have inflows, you have outflows. And in pre-development conditions, the inflow equals the outflow, and you're in an equilibrium condition. So what happens when you start pumping? Three things are going to happen. You're going to decrease storage, you're going to increase the inflow, and you're going to decrease the natural outflow. And so what we have here is capture is the increased inflow plus the decreased outflow. So the pumping is not only depleting storage, it's also capturing some water that otherwise would have gone elsewhere. Capture was a big part of a paper that John Bredehoeft wrote in 2002 that talked about the link between capture and groundwater modeling. But he did note that the concept of capture was first noticed by Tice in 1940, and that it's a dynamic process. And so basically what's happening is as you pump a well, a groundwater system will tend towards a new equilibrium after an initial decline in storage. And that equilibrium is caused by the increased inflow and the decreased outflow. That's the capture component. So the groundwater model is the perfect tool to study the dynamic nature of capture because we can extend our observed data. Some of the things Tolman talked about is you didn't have enough data. Well, the model helps fill that in. The model also provides an opportunity to experiment with different pumping scenarios and different hydrologic conditions. So let's look how we applied this in GMA 11 for the new DFCs that were just adopted and using the new groundwater availability model. For this, we use ModFlow 6. I think it's the first one that the board is using now that is used ModFlow 6. We use the nested model grid. So the smallest grid cells are now 10 acres, where before all the GAMs were basically at 1 square mile grid. Now we have the ability to have nested grids and smaller cell sizes in areas of importance, and in this case, it's near surface water features. We have direct cell connections in all the aquifers. That's something that we could not do in the old ModFlow codes. And we're going to look at groundwater budgets and hydrographs from this. So you've seen this, the steeply dipping aquifer of the Carrizo, Wilcox, Queen City, and Sparta. And in the surface, you've got all the different aquifers outcropping at different places. And from a conceptual model standpoint, we're seeing all the inflows and outflows between connections. But the interesting thing is on the left side, you'll see the stair step. There's always that surficial component. in each one. And that was always a limitation or a problem that had to be overcome in the old codes. So here we see how all the river cells that we use that follow the drainages. And so we created a top layer that's just the alluvial layers that are on the order of 50 feet thick. And you can see the nested grid there in the upper right, where in the areas of the streams, they're 10-acre cells, and they grow to 40 acres and larger as you move away from it. So here we're seeing the thickness of the alluvial layer between 10 and 80 feet. And we can see what areas are gaining and losing streams based on the model output. So this gives us the ability to look at inflows and outflows from each layer. Now, the Carrizo is a surface layer, but it's also a down dip layer. And you'll see that yellow bar, the blue at the bottom is the recharge on the surface, but the yellow represents the inflow-outflow relationship between that alluvial layer, the superficial layer. So we want to look at that in a little bit more detail. And so for the DFC work, we have we use the calibrated model from 1981 to 2013. And then we have the basis for the new DFC, which we called Scenario 33, that ran from 2014 to 2080. And we assumed a very significant increase in pumping from GMA-wide from about 130,000 acre feet to over 380,000 acre feet. And it's these simulations that provide the basis to understand the impacts associated with that increased pumping. So again, in the lower right, we'll see our little diagram of we're turning on the pumping in our little groundwater budget cartoon. And you can see from 1980 to 2013, pumping of about 130,000 acre feet, and then boom, Scenario 33, it bumps it way up. So what are the impacts of that from a water budget standpoint? Here's the storage change. The historic change bounces up and down, and then when the pumps start turning on in the simulation, it drops significantly and then starts to come back up. Well, that recovery and that flattening out is because that's as the capture starts kicking in. And that capture is composed of the increased inflow. We can see how the inflow is induced as a result of Scenario 33. And we can see how the natural outflow has decreased as part of Scenario 33. So this all looks good in a cartoon form, but how do you deal with this quantitatively? Well, that's where you get into water budgets. So here's the water budget for all aquifers in GMA 11. And we look at the inflow components, the outflow components, the storage change, and we're looking at two different time periods, the calibrated model from 81 to 2013, and the simulated period from 14 to 80, and then we're going to calculate the differences between those two. So we can see from a pumping standpoint, we're going from that 130,000 to the 385. That's an increase of 255,000. What happens as a result of that? Well, storage change is relatively small, only about 8,000 acre feet on average. The inflow increases about 161,000. And then the natural outflow components are fairly substantial, but not significant like the inflows are, and certainly higher than the storage change. So we can take that pumping number, 255,000 acre feet, that's the pumping increase, and we can break it down. The storage reduction, broken out into confined and unconfined, works out to a little over 3%, there on the far right, of the total pumping increase. What does that mean? Well, this is one of the wells. This is a location of a Upper Wilcox well in Rusk County. And we can see the model predictions of the drawdown from 2013. It sort of bounces around. And then before 1980, and then when the pumping hits, you get this big drop, and then it starts to taper off. It levels off. It's reaching a new equilibrium. The induced inflow represents about 72%, or the induced inflow from the alluvium represents about 72% of that total pumping increase. The alluvium is tightly connected to the stream flows, and so a good chunk of that is actually coming from surface water, because there's very little storage within the alluvium. ET is decreased by about 15%. That's part of what's supplying that increased pumping. So we can summarize that by looking at the increased inflow from the alluvium. That's your surface water impacts. From 81 to 13, this is a net gaining area. Net flow was from the groundwater to the alluvium and then ultimately to the rivers. From 14 to 80, it's now a net inflow from the alluvium. The alluvium is becoming a recharge source to the groundwater, to the new wells. We also see some substantial decrease in the groundwater ET. And the minor insignificant components include the increased inflow from the overlying formations. That's, in this model, that's the Awa-Jackson. And there's minor changes in lateral inflow from Arkansas, Louisiana, GMA 8 and GMA 14. So how much are we talking about? Well, the alluvium, 72% of that increased pumping. ET is about 15%. All the little ones combined are about 10%. And what's missing here? 3% of the increase in pumping is supplied, if you will, from storage. So the total estimated recoverable storage doesn't really apply here very much, because you can pump and pump and pump, and you're not going to really make a big dent in the pumping or in the storage. So to summarize, we looked at a scenario called Scenario 33 that bumped the pumping from 130,000 acre feet to 385. We created a new equilibrium condition. There's minimal storage change after about 30 years, and the constant groundwater levels after that initial decline. And that's all because of capture. That capture comes from the increased inflow, primarily from surface water. The decreased natural outflow, the old base flow to the river, and now it's actually a recharge source. And here's several references that may be of use to you down the road. And with that, I'm happy to answer any of your questions.
So basically what you're saying is all the surface water flow, a lot of it is going to be diminished as a result of this potential pumping in the future. What do you think that's going to do to the surface water right holders?
Back in 2009, when the environmental flows process got started, and we were just finishing up the first round of the DFC process, I was asked a question about that, and I said the two processes are like two trains on non-parallel tracks. They're going to crash into each other at some point. So there is the potential for having impacts on surface water rights. You'll start seeing more calls because there'll be diminished flows as pumping goes up. The problem here is that there have been some that have tried to explain or tried to sell groundwater pumping in rural areas as like a free lunch, like free water. They should just get it and move it, but there's other impacts associated with it. I can't hear you. There's noise back here, so it's hard to hear you.
I was wondering if you see the trends for gauging stations, how did you inform the model which river cells were gaining or losing?
Yeah, the gaining and losing cells you could extract that information out, but as a regional model that wasn't exactly calibrated for that, it'd be only general information. And this is a regional model, when you're looking at a specific project or something, that would require some more detailed, refined calibration in those areas. And then you could actually get a better handle on that. But a lot of that is going to rest on good data. And that's one of the limitations of being able to do these kinds of models on a local scale basis. Right, and that's one of the assumptions that you're making is how much water is in the stream and how much of that is available. That's one of the big advantages of the new model and model codes is that we have a much better ability to make sure that that is properly constrained. But yeah, that's a concern. For that kind of a detailed analysis, you'd have to decide whether the stream, it's through stream regulation or is it because of historic groundwater pumping that the streams are lower. It's a vicious cycle. So you have to take that into account. Yeah, in this particular model, we didn't get into that level of detail because we were stuck with our regional data and a regional focus. And so the approach here was to more highlight what the potential impacts are, because the only way you're going to be able to do this with any real degree of specificity is on a local scale. But that's when you have to look at actual data of what the stream flows are. We calibrated this in general versus a base flow, that based on the best information that we had on a regional basis. Right, those are great questions. I talk about it in the explanatory report in the context of this could lead to issues with surface water depletions, stream flow depletions. On a specific district permitting thing, that's something that each district will have to deal with down the road. The impetus for having this big increase in pumping was driven by the regional water plans. We couldn't, even the new model, we couldn't reach all the old availability numbers and needs. And so there was going to be another cycle of this when Region D and Region I get this information and how they're going to deal with it, because it may have an impact on their ability to supply their strategies. But those are all issues that are going to have to be dealt with. Yeah, the recharge was only the difference between the actual average and the average that I used in the simulations. It basically is it's the same. Yeah.
Did you simulate any drought variability in that system that might change stream flow over time?
Right. The way we run the DFC simulations is we assume average conditions, because we can't assume or know when the droughts are going to occur. And so it's just an artifact of how we do that. It certainly could be done to see what impacts the drought have, but then you have, is the pumping going to increase as a result of the drought? You're getting into a whole spinning yarn of how you would have to deal with that. So we're very explicit. We're just basing that on average conditions, because at this point, just getting the idea of a new equilibrium and not getting it complicated with other things is a big enough step, I think. Yeah, that's good. I do this same kind of analysis on all the GMAs I work on, and I work in 5 different ones from west to east. And you still see the same concept, but in some of the areas, the models are not as robust, and so the results are far less reliable. But my hope is that as the models improve over the next 5 to 10 years, that this is one of the key features that we could at least use this approach and this technique to at least on a first level address or identify what the problem is. Maybe not address it or solve it, but at least let's see what it is first. But yeah, you still see this sort of, I did this in Valverde County, the same approach with a model I developed there. Same thing, storage is not the issue, it's capture. And so the idea of going out and developing big groundwater projects to get all this storage is really not going to happen. Physically, it's not going to happen. Thank you very much. Appreciate it.